All right, everyone. We are here for the last part of chapter 14, which is going to talk about how we handle changes in variable with triple integrals. All right, so we're going to talk about the common variable changes, and then we're going to generalize that. So starting off, we're going to talk about two coordinate systems that we learned back in chapter 11, section 11.7. So if you want a refresher on cylindrical and spherical coordinates, at least the basics, it might be good to go back and view that video. With that said, here I'm reminding you what the conversions look like for different things, right? So for cylindrical, remember the x and y are essentially just transformed the same way they are with polar. The z coordinate is completely unchanged. When we write a coordinate out in cylindrical coordinates, we give a point as r theta z. So remember that's kind of like if I'm in the three-dimensional space, right? I'll go out an amount. That'll be the r. I'll go around a certain angle. That'll be the theta. Nope, nope. We are not having a kitty lesson today. Come on. Uh-uh. You can nap here later. Oh no. Okay, cattail. No biggie. All right, but anyway, we've got come on, go on. I know. You just want to nap. Silly kitty. All right. Anyway, um when we're in cylindrical coordinates, remember you go out an amount, that's your r. You go around an amount, that's your theta. And then the z coordinate is just going up by an amount. So like from that point, you would go up, and this would be your point, r theta z. With spherical coordinates, it was a little bit more complicated because we first off had a completely different set of letters. First thing, talking about letters. Do not confuse this with mass density. Yeah, so we've been doing these problems where we look at moments of mass using a density function that is called rho, right? If um, if we come across a problem where we need both spherical coordinates and density functions, either it'll be obvious in the way I note things, like for example, density, I would write rho of x, y, and z, right? This rho is not a function of x, y, and z. Um, or I might just use a completely different letter. We will cross that bridge when we get to it. So in spherical coordinates, you have three different parameters. You have rho, you have theta, and then you have phi. Okay. So if I'm in a three-dimensional coordinate system, rho does not actually go out on the x-axis. I want you to think of rho as going straight up the z-axis. So you go up by some amount, that's your rho. Then you tilt downward some amount, that's going to be your angle phi. And then you go around some amount, that's your angle theta. I make my phi look more like a phi. There we go, I guess. Yeah. Anyway, that's what the plotting looks like for these different coordinate systems. What's going to be important for us in this section is being able to rewrite the differentials that we deal with in terms of these. So starting off with cylindrical coordinates, it's pretty straightforward, right? Because dv, which remember is our catch-all, I'm not saying an order for x, y, and z yet, differential when we do triple integrals. dv is in cylindrical coordinates the same thing as dz dA, right? So it's like your base area times the height. That's the volume in cylindrical coordinates. Now, if we remember what dA was for polar coordinates, and the reason I say that is because the only like cylindrical coordinates have a lot in common with polar coordinates, right? The x and y follow the exact same transformation. The z is just hanging out. So if I replace dA with what we learned about for polar coordinates, I end up getting this guy, which is our differential dv when we're working in cylindrical coordinates. So that is dv in cylindrical coordinates. Cylindrical. Such a weird word. All right. And then we'll do a couple examples that involve cylindrical coordinates, and then we will talk about spherical coordinates and all the things that ensue on that one. So first off, let's say we want to find the volume of a solid from a region Q cut from the sphere by the cylinder law. Okay. So a couple of things going on here. First, note it's asking us to find volume. We know that volume is going to be the triple integral over the base surface, right? dV. So that's volume, triple integral of dV. We need all of this information to kind of work through and figure out what the different bounds are that we're going to use for dz, dr, and d theta. Another thing, the next thing I want to point out before I write anything else down is that this equation of a sphere is given to us in rectangular coordinates. The cylinder is already given to us in technically cylindrical coordinates, right? But it looks like a polar equation. So it would be in my best interest to convert my rectangular equation to a cylindrical one, right? Remember, with cylindrical, you can't really do anything with z. It stays z. It's convenient. But we know that x squared plus y squared from polar coordinates is the same thing as r squared. So we can rewrite the equation of the cylinder as r squared plus z is equal to 4, or r squared plus z squared, I should say, is equal to 4. Now, this is already in cylindrical coordinates. We don't need to worry about that, but I do want to remind you of some of the caveats about setting up triple integrals. So the cylinder is given to me in terms of only one variable, right? It's a value of r in terms of theta. So what this tells me is that when I go to rewrite my dv, I'm going to use dr as my second differential, which means that the middle integral is going to have bounds from r equals 0 to r equals 2 cosine theta, right? Now we just need to figure the rest of this out. I will say that for this one, the theta part is probably going to be the easiest, right? And we have to remember something that I warned you should be comfortable with. R equals 2 cosine theta. If I were looking at that on a polar grid, what range of theta would be needed to trace this entire shape out? Hopefully you emphatically said pi, 0 to pi. Right, this is one of those ones that's a circle that goes in that direction, right? So if we talk about this as a cylinder, basically imagine the circle kind of shooting up and down above and into the paper, and that makes a cylinder. So since I only need to go from 0 to pi to trace this out, that's going to give me my bounds for theta. Because both of those bounds are numbers, I know that this is going to go on the outside, 0 to pi and d theta. All right. Now the last part, I know that my first differential is going to be a dz, and I know from here that dv is replaced by r times the three differentials. Okay, so now I have to figure out what my bounds for z are. If I were to go, yeah, if I were to go from this equation, I could actually solve for z and get my bounds for the dz differential. So I'll start by subtracting r squared from both sides. I get z squared is equal to 4 minus r squared. Okay, then I take the square root of both sides. I get that z is equal to plus or minus the square root of 4 minus r squared. Now, if I read the question carefully, it does not limit me to just above the xy plane or just below. So I'm going to actually use both of these roots when I write out my bounds. So we know that z is going to range anywhere from negative square root of 4 minus r squared to positive square root of 4 minus r squared. And we've set up the integral to find the volume, right? Triple integral of dv. That's all it was. And again, the r comes from the fact that we're converting to cylindrical coordinates, right? And here's the thing, whenever we change variable, we always end up having to multiply by something. That something has a name, and we'll talk about it at the very end. Starts with a J. It's always those J names. All right, so now if I go through and evaluate this integral, remember you start from the inside. So we have the integral from 0 to pi, integral from 0 to 2 cosine theta. I know the antiderivative for this is going to be ZR. And we're going to evaluate from Z equals negative square root of 4 minus R squared to positive square root of 4 minus R squared. Then we integrate with respect to R, then theta. Okay, now when I plug these in, what's going to end up happening is I'll have R times that square root minus negative, so plus R times the square root. So really I get two of them. So this will be the integral from 0 to pi, integral from 0 to 2 cosine theta of 2r times the square root of 4 minus r squared. And just to say it again, I got that 2 because we subtracted negative square root of same thing. Okay, and then we're integrating dr d theta. Now, when you look at this integrand, notice that you have an r squared on the inside of the square root, and you have just a regular r on the outside of the square root. That's a derivative pair, meaning that this looks like the derivative of that, right? It's not exact. It's off by a multiplying constant, but that's fine because we all took Cal 1 and we know how to do U sub. Here's the thing though, when we've already changed variable like this, you still have to remember the basics with U sub. Yes, you can call the whole thing under the square root U, but you have to remember that that's going to adjust your differential, and it may have you multiplying by a constant. And you also have to remember to adjust your bounds because you're changing to a different variable. So off to the side, I'm going to erase this circle. So I have space. Okay. So off to the side, I'll set up my U sub. I'm going to let U be equal to the radicand, the thing under the square root. When I take my differential, I get du is equal to negative 2r dr. The thing is, I don't have that multiplying negative in my integrand. So if I multiply or divide both sides by -1, I can rearrange this so that what I have on the right side exactly matches what I have in my integrand. Right? So I can directly replace 2r dr with negative du. And to make my life even easier, right? There's also a property that if you switch the sign on an integral, you can flip the bounds. So yes, we would write negative integral. I'm just going to write the integral quick. All right, so yes, I could write negative integral from 0 to 2 cosine theta. That would be correct. Actually, no, it wouldn't because I still have to adjust, right? But I'm actually going to end up switching the bounds so that the 2 cosine theta, once I transform it, is on the bottom, and the 0, once I transform it, is on the top. That way I don't have to write a negative, and I can keep my integral positive. So to transform, right, we're going to take each of the bounds that we have. So you have 0, for example, and plug 0 in for the r. Because remember, since this goes with the dr differential, 0, and 2 cosine theta are values of r. So if I plug 0 in, I get 4. Remember that was on the bottom, but now I'm going to put it on top so that I don't have to deal with the negative. You could just leave the negative if you want and put the 4 on bottom. It's not a big deal. And then if I transform 2 cosine theta, I'm going to get 4 minus 4 cosine squared theta. Right? And if I factor a 4 out, it'll be easy for me to see that I can use a trig identity to make this even simpler, right? Because 1 minus cosine squared theta is just sine squared theta. True story. So for my bottom bound, I'm going to write 4 sine squared theta. Okay, so now I've adjusted my bounds. I can make my substitutions using what I wrote up here. So 2r dr collectively will be replaced with du, not the negative because we flipped the bounds. And wherever I see 4 minus r squared, that gets replaced with just u. So we have the square root of u du. And then there's still our d theta that we have to deal with after this. So remember, when you're integrating square roots, you can always write that as a power. So when you find the antiderivative, you're just doing your power rule. So outside integral still untouched. Add 1 to the power, I get u to the 3 halves. Or divide by the new power. That'll be divided by 3 halves or times 2/3. And we're going to evaluate this from u equals 4 sine squared theta to 4. And then integrate with respect to theta. I go ahead and box all this part off so that we can focus on the integral. Okay. So at this point, all I'm doing is I'm plugging these numbers in for the u. So I still haven't taken that outside integral yet. If I plug 4 in, thing to remember is do the denominator first. Since this is over 2, that's the same as saying take the square root. Square root of 4 is 2. Then I apply the numerator. 2 to the 3rd, I get 8. So 4 to the 3 halves is equal to 8. If I multiply that by 2/3, I get 16/3, right? Because 8 times 2 is 16. Right now for the bottom bound, apply the denominator. If I take the square root of 4 sine squared theta, I get 2 sine of theta. Now if I cube that, I would get 8 sine cubed theta. And then if I multiply that by 2/3, I get minus 16/3 times sine cubed theta. So I can factor out a 16/3. And I can remember that when we were Cal 2 students, we learned how to deal with odd powers of sine like that. Remember, you can always rewrite sine cubed theta as sine theta times sine squared theta. Right? And well, sine squared theta can also be written another way that hopefully we all are just screaming at the screen right now because I'm taking so long to say it. We can rewrite sine squared theta as 1 minus cosine squared theta. So ultimately, this is going to be minus sine theta times 1 minus cosine squared theta. Oh my God, that is a mess. Okay. So what I'll do next, switching over to my notebook. I ran out of space. Okay. So what I'll do next is I will distribute the sine theta to both of these terms. So at this point, we're up to 16 thirds times the integral from 0 to pi of 1. That's the one that's left over from here. Distribute, I get minus sine theta. Distribute, I get plus, because negative times a negative is positive, sine theta cosine squared theta. Okay. Now the antiderivative for the first two terms is pretty straightforward. All right, we get 16 thirds integral from 0 to pi. I'm going to go ahead and not write the integral yet. My bad. Okay. So we're going to take our antiderivative for the first two terms, right? Antiderivative of 1, we get theta. Antiderivative of sine theta is negative cosine theta. But since there's already a minus there, that will become plus cosine theta. We'll evaluate those terms from theta equals 0 to theta equals pi. And then we have the leftover here. So one thing you might notice is that cosine theta and sine theta make a derivative pair, right? Sine theta looks an awful lot like the derivative of cosine theta, right? It's off by a multiplying constant, but that's okay. So to kind of make this a little more obvious to see, remember, anytime that you have trig to a power like this, you could always write it like so, right? So now you see you have a cosine, you have a sine, derivative pair. So we can do a u sub. Since I already used the letter u though, I'm going to use a different letter. Let's say v. So I'm going to let v be cosine of theta. That means that dv is negative sine theta, but I don't have the negative in my integrand. So I'll move it over. So we get negative dv is equal to sine theta d theta. Then, of course, we have to transform our bounds. So v evaluated at 0 will be cosine of 0, also known as 1. And v evaluated at pi is going to be cosine of pi, also known as -1. So our bounds would be 1 to -1. It's kind of weird. So I'm going to switch it and write -1 to 1. And because of that, I'm going to switch the sign, right? Since we would be adding the negative from the dv, that would just become a positive, right? So then our integrand is just going to be u squared du. Pretty simple one, not u, v. My bad. There we go. Okay, so going on to our next step, I'm going to go ahead and evaluate these guys. So we have 16 thirds. If I plug in pi minus 0 for this term, I get pi. Now for cosine, if I plug pi in, I get -1. If I plug 0 in, I get 1. Okay, and then we'll simplify that in the next step. For this one next, we are going to use our power rule. Add 1 to the power, v cubed, divide by the new power 3, and evaluate from v equals -1 to +1. So then here we have 16 thirds multiplied by pi minus 2. And now plugging these v's in, right, I would get 1/3 minus -1/3. So 1/3 plus 1/3. 2/3. So if I were to distribute the 16 thirds, I would get 16 pi over 3 is one of my terms. I would get -32 over 3 as the other. But I can combine that with this 2/3. That's going to end up giving me -30 over 3, which is more affectionately known as 10. And that's our answer. Look at us. We found a volume using cylindrical coordinates. Amazing. Now we'll go on to another example where we're finding mass. So for this one, we have an ellipsoid that we're calling Q. We have the equation of the ellipsoid, and we are told that we are staying above the XY plane, which is going to be important when we're setting our bounds up. It tells us next that the density at a point in the solid is proportional to the distance between the point and the XY plane. So I want you to think about something real quick. If I have my three-dimensional Cartesian rectangular coordinate system, remember the floor here is your XY plane. So the distance away from that at any point is literally just its Z coordinate. All right, so if the density is proportional to the Z coordinate, another way of writing that is that rho of XYZ, and this is in cylindrical, not in spherical, so we're not going to worry about the weird distinction there, is equal to some constant that we're going to call K times Z, the distance between the point and the XY plane. So that's our density. We want to find the mass. So remember, mass is the zeroth moment or just the integral of the mass density. So essentially, all we're doing is we're finding the triple integral over the region Q of kz dv. So now we need to set up our bounds. All right, so keeping in mind that this is the same ellipsoid that we looked at in a different section. Yep, this was the one where we found the volume of plankton. All right, we remember that essentially this is going to be tall on the z-axis and basically circular on the xy plane. So when I go to set up my cylindrical coordinates, remember the r and the theta, the r and the theta are only going to apply to this circular piece, right? The z coordinate we already know is going to depend on what we get over here. All right, other thing to note is that we are using cylindrical coordinates to set this integral up, which means that I can actually rewrite this guy in terms of r, theta, and z. So with those first two terms, I can factor a 4 out. Okay, we know that x squared plus y squared in cylindrical / polar coordinates is r squared. And we know that we want to solve for z. So I'm going to subtract 4r squared from both sides. And then I'm going to take the square root of both sides. Now, for this one, I'm only going to consider the positive root because in the question, it told us to stay above the xy plane, meaning that we are only going to consider z coordinates that are positive. Uh-oh. I think I have to go save a cat real quick. Getting into something. Where'd we go? Pause. That is life when the cat can get under the bed but can't get out from under the bed. All right, so anyway, back to our question. We figured out the bounds for z, right? So in the last example, we ended up having something that was positive and negative. Here we're not, because again, the problem tells us that we are staying above the xy plane. So my bounds for z are going to be 0 to square root of 16 minus 4r squared. And the thing about that is that that relies on r, which means that when I set up my dv, the dz part is going to have to come before dr. Now, the base part of this ellipsoid in the xy plane, we mentioned that was a circle, right? Specifically, it's a circle that is centered at the origin that has a radius of 2. right? And if you weren't sure by just looking at that, remember, if I want to get the information like the radii in each direction for an ellipsoid, I need to write in standard form. So if I divide every term in the equation for the ellipsoid by 16, I end up getting my standard form, which tells me that in the x direction, the radius is 2, the square root of 4. In the y direction, the radius is 2, and in the z direction, the radius is 4, right? So the z coordinate at the top would be 4, and then for the x and the y coordinate, they would all respectively go out to positive and negative 2. Now, this brings up some options that we have for setting up the r and the theta. Well, actually, before I do that, getting ahead of myself. Um, we do need to write the equation of this circle in polar coordinates. So if I have a circle that is centered about the pole with a radius of 2, in polar coordinates, that would be r equals 2. So here's where we would have options. I could make this plus or minus 2, but that would affect what I can choose for theta. If you think about this shape in polar coordinates, we go out 2 and we go around from 0 all the way back to 2 pi to trace the entire circle out. So if I let my radius be from 0 to 2, then my theta will range from 0 all the way to 2 pi. But if I let r be positive 2 or negative 2, then I would only be able to rotate each of those by a half of a circle. So to keep it simple, I'm going to let r go from 0 to 2, and I'm going to let theta go from 0 to 2 pi. Plus, it's always nice when you have 0 as one of the bounds on your integral. So with that said, z depends on r. R doesn't actually depend on theta. Theta doesn't actually depend on r. So the order for those two doesn't really matter, right? But to get us in the habit that we typically are going to need to do, I'm going to go dz, dr, d theta. So setting up my bounds, I know d theta is my outermost. We said that was going to range from 0 to 2 pi. I know r is my middle one, ranges from 0 to 2. Z is my innermost. And remember, we're only above the XY plane, so we go from 0 to that. So square root 16 minus, make my one more evident there, 4r squared. All right, and then the integrand was just our density function rho, so kz dv. And because we're in cylindrical coordinates, remember we have that extra factor of r that comes about from replacing the differential. So r and then our three differentials in order: dz, dr, d theta. Okay, and then we basically are going to go through and we're going to do an integral that looks an awful lot like the one that we did in the last example. So I am going to just give us the answer for this one so we can move on to the next part. And we end up getting 16 pi times the constant k. All right. So now that we've done that one, we know what the mass of that ellipsoid would be. Reminder, we could take this further and calculate center of mass by looking at the moments along each of the three different planes and normalizing by dividing by the mass. Right? We could also find moments of inertia by looking at the second moment, but we're not going to do that because time. So now that we've done a couple examples looking with cylindrical coordinates, let's talk about spherical. So spherical coordinates are a little bit more complicated. As I mentioned before, you start off by going up the z-axis by some amount rho, then you kind of tilt outward from the z-axis by some angle phi, and then you come around by some angle theta, right? So rho is the length, theta is how far you go down. No, phi is how far you go down, and then theta is how far you go around. I like to think of it as like those laser security systems at the high-end museums that collect all that protect all the ancient artifacts, right? You shoot the laser beam up, comes down the wall a little bit, and then it goes around and sweeps the perimeter. So with spherical coordinates, that's what our differential replacement is. So anytime that I rewrite an integral in spherical coordinates, I'm going to replace dv with rho squared sine phi d rho d phi d theta. And if I just said the name of your frat, you have to take a shot of espresso. Hmm. Gotta keep alert, you know. Anyway, now that we've got, now that we know what that differential is going to be, we can set up some integrals in spherical coordinates. First example, we want to find the volume of a solid region Q. So immediately, volume is going to be a triple integral over the region Q dv. That's the definition. That's what you start with. We already know that if we're going to convert into spherical coordinates, and I'm going to leave some space, although technically it's not a big deal if you write the differentials first. If you're a physics or engineering major, then you will very quickly learn that that's a thing they do, right? But I already know that somewhere in my integrand, I'm going to have this factor multiplying my differentials. So I'm going to start by just writing out this, because if I don't write it out now, there's a good chance that I'll forget to write it. And you don't want to be the person that does that on the exam. Because oftentimes, if you forget to write that, the integrals turn out way nastier than they actually should be. So always make sure you write those factors down. Right. For cylindrical, it was the R. For spherical, it's rho squared sine phi. For polar, it was just R. Right. In general, it's the E, and we're going to talk about that later. All right. So anyway, we have to figure out how we're going to write the region Q. So Q is bounded below by the upper nap of a cone. So when they say upper nap, this is what a cone looks like. The upper nap is just this circle at the rim, right? It's the rim. So think of it as like the rim of a fancy glass you see at bars. And we're bounded above by the sphere x squared plus y squared plus z squared is equal to 9. And if you remember, that is a sphere that has a radius of 3 and is centered at the origin of the XYZ coordinate system. So basically, if I were to draw this, I'm going to make the back of the cone dotted to give the illusion of depth. Story of my life. All right. So if you think about it, we're really just trying to find the volume of this shape. It's like a turtle shell or the top of a really full pie, right? Or like Goku's backpack in Dragon Ball. Right. But anyway, that's what we're trying to find the volume of. So we need to use the information that we're given here to convert everything into these different spherical coordinates uh, that we have for the differentials. So a couple considerations here. First off, if you remember from back in chapter 11 when we discussed spherical coordinates, you might remember this conversion that rho is equal to the square root of x squared plus y squared plus z squared. Remember, that was kind of just an extension of what we learned about with polar and cylindrical. Right, so if I see the inside of that square root in any of my equations, I immediately can replace it with rho squared. So we get rho squared is equal to 9, which means that rho is equal to plus or minus 3. Now, again, this conundrum that we come to when we have these pluses or minuses, all depends on what you end up choosing for the different angles. Remember, theta is the angle that you use to sweep around. Since the intersection of the upper rim of the cone and the hemisphere or the sphere, right, is a circle, then the easy choice would be to let theta be from 0 to 2 pi and only choose values of rho that are positive. Remember, you do have that other option where you only trace out half the circle and use both the plus and the minus. But we love having 0 as one of the bounds on our integral. So yeah, so we're going to say that rho is going to range anywhere from 0 to 3. By extension, theta is going to range anywhere from 0 to 2 pi. Okay, all that's left now is to figure out phi, right? So remember, rho is the length of the laser beam that goes all the way up to the top of the sphere. Theta, once we've gone out by however, whatever the angle phi is, theta tells us how many radians we sweep around, right? We've already figured those two things out. The only thing I need to figure out now is the angle between um, basically these two. And to help me figure that out, I need to know about the intersection between the sphere and the cone, right? So there are a couple of ways I can do this. In my opinion, the easiest way is to note that the equation for the cone literally gives me something that I can replace z squared with. And the equation of the sphere has a z squared in it. So the easy approach there is to just replace the z squared with the right side of that equation. All right. And from there, we end up getting that x squared plus y squared is equal to 9 halves. Now, if you remember from spherical coordinates, there kind of was a relationship between the rho that we use for spherical and the r that we used in polar and cylindrical. Remember, it made this kind of right triangle where you have your z coordinate, you have the length rho, and you have the radius in the xy plane r. Right? And this, of course, makes a right triangle because the z coordinate goes directly up. So we know that rho is equal to 3. Based on this, we know that r squared is equal to 9 halves. Yep. So if I take the square root of both sides and only consider the positive root, I get 3 over the square root of 2, right? Square root of 9 is 3, square root of 2 is square root of 2. So if I want the angle phi, I have to remember rho is going straight up, right? And then it's coming out by some angle. So this is the angle phi that we're looking for, not this, this. It's actually complementary to, yeah, it's actually complementary to this angle, which means that it actually would be equivalent to the other one in the right triangle. So with that said, I know the opposite side of phi, I know the adjacent side, or the hypotenuse of the triangle. So essentially, I can figure out what the value of phi is, at least at the furthest out point, right? Furthest out point, by setting sine of phi equal to opposite over hypotenuse. So that would be 3 over the square root of 2 divided by 3, which is 1 over the square root of 2. And because this is a unit circle one, right, you might rationalize your denominator and get that this is equal to the square root of 2 over 2, which means that phi at the point that's furthest out from the center or from the top of the sphere would be equal to pi over 4. Right? So that means that phi for any point in this three-dimensional object is going to be somewhere between 0, that's this part, and pi over 4. Right? And you might be thinking, well, wouldn't we go like from negative pi over 4 to no, because you remember also take theta into account, and that gives you what you would get from the negative value of phi. So with that said, we have all of our different ranges for everything. So because all of them are constant, it technically doesn't matter what order I write my differentials in, right? But good habits. Let's do d rho, d phi, d theta. So I know that rho is going to range anywhere from 0 to 3. D rho. I know that phi is going to range anywhere from 0 to pi over 4. 0 to pi over 4, and then put my d phi. And then I know that theta, as we mentioned, is going to range anywhere from 0 to 2 pi. And then I write my d theta, and I have my complete integral to get the volume. So at this point, integrating that would actually be relatively straightforward. All right, so we get 0 to 2 pi, integral from 0 to pi over 4. Just to remind you, this will become rho cubed over 3 sine of phi. And we would evaluate from rho equals 0 to rho equals 3 d phi d theta. Once I do that, I can evaluate at the endpoints, and I would get 9 sine of phi, right? Because 3 cubed divided by 3 to the 1 is 3 squared, also known as 9. So we get integral from 0 to 2 pi, integral from 0 to pi over 4 of 9 sine of phi d theta. All right, so at this point, I know the antiderivative of this guy pretty easily. Right, that's going to be negative. So I'll go ahead and take negative 9 out. Integral from 0 to 2 pi of cosine phi, evaluated from phi equals 0 to phi equals pi over 4. And if we wanted to, we could do that thing again where we switch the bounds. And the reason I would do that is because I know cosine of 0 is 1 and cosine of pi over 4 is less than 1. So if I wanted to, I could do that. I don't have to, but I can. Either way, you would end up getting the following. So I'm going to take this negative out, right? And we would get 1 minus the square root of 2 over 2, right? Also known as 2 minus the square root of 2, which means that whenever I integrate this with respect to theta, we're going to get 9 halves times 1 minus the square root of 2 times pi. And that's the value of the integral. That gives us the volume of that shape. And textbook actually gave it as a decimal answer. Oh, it was 2 pi. Whoops. So we would multiply that by 2. Yep. So we'd end up having 9 pi times uh, 1 minus the square root of 2. No, I messed something up. Hmm. Anyway, so we end up getting our volume, and that is how you do that one. Next one, we want to find the center of mass of the solid, of the exact same solid. Right, so we're still looking at this sphere cut off by the rim of a cone, right? That's still the solid that we're looking at. The next thing we want to do is find the center of mass, which remember involves the first moment of the density function. So before I get into like super heavy calculations, getting three different moments and then blah, 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 read the question. So we want to find the center of mass of the solid region Q from the last example if its density is uniform. I want you to look at this shape again. All right. I want you to remember that the sphere was centered at the origin. So this whole shape is completely symmetric about the z-axis. Because of that symmetry, we know that the center of mass is going to be somewhere along here, right? Somewhere between the top and the base, right? There's not going to be any deviation in the x or y direction because of the symmetry and the fact that this is uniformly distributed, right? This is an assumption I can only make because the density is uniform. If the density were variable, I could not make any assumption, and I would need to do what we learned in the last video about finding moments. With that said, I know that the center of mass is gonna have x and y coordinates of 0. I just need to figure out what the average z coordinate is. And I can do that by looking at the moment along the xy plane. So remember how this works. It's basically our integral. In this case, it was our triple integral along the region Q of z, right? That's the variable that's left out, times the density function. And another interesting thing is that if the density is uniform, then rho xyz, the density, is just a constant k. So z times k dv. Oh, yeah, I forgot that we still need to do mass. Oh well. All right, so to set this integral up, all right, we're going to take the same setup that we did when we set the integral up for region Q in the last example. So we're going to have 0 to 2 pi for our d, what's it called? Theta. We're going to have 0 to pi over 4 for our phi, and 0 to 3 for rho. K is a constant, so K can come out in the front, and I need to not forget it. All right, then we have Z, and then we're going to replace that. Actually, I can't write Z because we're in spherical coordinates. So instead of Z, I'm going to write the equivalent of Z. So remember, in spherical coordinates, Z is rho times cosine of phi. So instead of writing Z, I'm going to write rho cosine phi. And then we have our differential that we set up for this as well. So remember the rho squared sine phi cannot go anywhere, has to stay there. And then we have our differentials d rho, d phi, d theta. So if I were to simplify that, we would get k times the integral from 0 to 2 pi, integral from 0 to pi over 4, integral from 0 to 3 of rho cubed, right? Multiplying those times cosine phi sine phi. And don't write anything more yet because I can use a trig identity to make this easier so that I don't have to do some weird u sub for no reason. All right, remember this is similar to your sine double angle formula. And to remind you of what that was, we have sine of 2 phi or 2 theta or 2 whatever you want to call the angle is equal to 2 sine of phi cosine of phi. If I have sine of phi cosine of phi, then that would be half of sine of 2 phi. So I'm actually going to erase what I wrote here and write a simpler version of it. So the 1/2, because I have to divide that by 2, can go out with the k. And the rest of this can just be written as sine of 2 phi. All right. And then we have our differentials d rho, d phi, d theta. So now we're evaluating a pretty simple triple integral, right? Look at your innermost integral. It's with respect to rho. So this guy doesn't affect anything. We're just doing power rule on rho cubed. So I have k over 2, integral 0 to 2 pi, integral from 0 to pi over 4 of 1/4, which I will take that 4 out here and write an 8. Rho to the 4. We're evaluating rho from 0 to 3. Then we have our other differentials to work with. So when I evaluate that, 3 to the 4 is 81, 0 to the 4 is 0. So this just becomes 81, which is a constant, which can also come out front. So now we have 81k over 8, and we're taking the integral from 0 to 2 pi of the integral of d phi, which would just be phi, evaluated from phi equals 0 to phi equals pi over 4, d theta. And when I evaluate that, guess what? I end up getting pi over 4, which is also a constant, which can come out front with the 81 over 8. So now we have 81k. We have pi over 4. 4 times 8 gives me 32. And then we're just taking the integral of integral from 0 to 2 pi of d theta, or 1 d theta, which would just be theta evaluated from 0 to 2 pi. So I end up with I missed a 1/2 somewhere, didn't I? Oh my gosh, I completely forgot. No wonder that turned out weird. Yeah, y'all. Backtrack. I forgot to write sine of 2 phi. Okay. So sine of 2 phi. Um, yeah, so we're gonna end up getting our 81k over 8. All right, but this time we're taking the integral of sine of 2 phi d phi. Right. Yeah, because the part that we get from evaluating rho is still going to be 81, right? So we can still pull the 81 out front like we did here. So at this point, we're doing the integral of sine of 2 phi d phi. So we get 81k over 8 times the integral from 0 to 2 pi. All right, and then here we know that the antiderivative of sine is negative cosine. And because I have a coefficient of 2, I'm going to have 1/2 cosine of 2 phi. And we're going to evaluate that from phi equals 0 to phi equals pi over 4. And if you want, you can flip those bounds and take the negative away. The same reason cosine of 0 is bigger than cosine of pi over 2. And we're going to integrate that with respect to theta. Erase this identity. Give us some more space. Space goes, goes. All right. So anyway, when I plug pi over 4 in, I'm taking cosine of 2 times that. So cosine of pi over 2, guess what that is? That's 0. Then when I take cosine of 0, guess what that is? That's 1. So we get 0 minus negative 1/2 times 1, also known as just 1/2. So I can take the 1/2 outside to multiply the 8 in the denominator. I get 81k over 16. And then we're taking the integral from 0 to 2 pi of 1 d theta, right? Which is going to result in 81k over 16 multiplied by 2 pi minus 0. So to make this a little easier on myself, I can reduce 2 over 16 to 1 over 8. And basically I get 81k pi over 8. Keep in mind, though, that is not our z coordinate. We still have to divide by the mass that we got in the last, or the mass that we actually didn't calculate. So we'll need my notebook again. All right. Luckily, the mass is actually a really fast one. So for this one, whoops. Remember, your mass is equal to the triple integral over the region Q of your density function, right? dV. For us, we knew that the density function was just K because the density was uniform, which basically means that for this one, the mass is going to be equal to K times the triple integral because that's a constant. I can pull it out front of the integral. And guess what this is, y'all? It's the volume. And guess what we found in the last example? We found the volume. So this is literally just going to be K multiplied by the answer that we got in the last problem. So it was 9 pi times 1 minus the square root of 2. Now, now that we have the mass, we can get the z coordinate for our center of mass by taking the moment along the xy plane divided by the mass. Moment from xy plane was 81k pi over 8, and the mass was k, we'll actually just say 9 pi k times 1 minus the square root of 2. Now for this one, a couple things are going to happen. First off, 81 over 9, that simplifies to 9 over 1. Second off, k's are going to divide out. Third off, pi's are going to divide out. So I literally end up getting 9 over 8 times 1 minus the square root of 2 as my z coordinate, which means that my center of mass, x bar, y bar, z bar, is going to be equal to 0, 0, 9 over 8 times 1 minus square root of 2. And there we go. That's the center of mass. All right, and that's all I'm going to say about the common cases with spherical coordinates and cylindrical coordinates. The next part, I guess I will go ahead and put in a separate video. So you can take a break, stretch your legs, and try to draw plankton. Happy mathing.